A philosopher died 2,000 years ago, and we're still arguing about whether you can cross a room. Not whether you should, but whether you physically can. Zeno of Elea created puzzles so frustrating that mathematicians spent millennia trying to solve them, only to realize the solutions might be missing the point entirely. His arguments broke reality into pieces so small they vanished, then asked why anything exists at all. The year is around 490 BC. Southern Italy isn't Italy yet, just a collection of Greek colonies clinging to the coastline, trading posts that became cities, experiments in living far from home. Elea sits on the western coast, below what will one day be Naples, a town small enough that everyone knows everyone, but connected enough to the wider Greek world that ideas flow through like trade goods. This is where Zeno is born, the son of Teleotagoras, a name we know only because ancient writers bothered to record it. Everything else about his childhood is speculation, gaps in the historical record that will never be filled. What we do know is that Elea had something most Greek colonies didn't, a philosopher who would change how people thought about thinking itself. Parmenides had already established the town's intellectual reputation by the time Zeno was old enough to study. The Eleatic school, as it would come to be called, wasn't a physical building with classrooms and lectures. It was more informal than that, a gathering of minds around a radical idea that seemed to contradict everything the senses reported. Parmenides taught that reality was one thing, indivisible, unchanging, eternal. Everything else, all the diversity and motion and change you experienced every day, was illusion. Being was, non-being wasn't. Change required non-being, so change was impossible. Try selling that idea to someone walking through a marketplace. The fish are rotting, the fruit is ripening, the sun is moving across the sky. Change is everywhere. But Parmenides insisted it was all appearance, all misinterpretation of something deeper and stranger than human senses could grasp. Most people would have dismissed this as the kind of nonsense philosophers say to sound clever. Zeno didn't dismiss it. He became Parmenides' student, then his friend, possibly more than that if Plato's gossip is accurate. The relationship between them was close enough that later writers called Zeno the adopted son of Parmenides, though whether that was legal adoption or just affectionate description is unclear. Here's what made Zeno different from his teacher. Parmenides had stated his philosophy, explained it, tried to help people understand why reality must be one unchanging thing. Zeno didn't bother with explanation. He went on the attack. If you think multiple things exist, prove it. If you think motion happens, demonstrate it. And then he'd systematically destroy whatever proof you offered, showing how it led to contradictions so absurd you'd have to abandon your position. This was new. Previous philosophers had described their worldviews, built systems of thought, offered wisdom. Zeno built logical traps, arguments designed to catch you no matter which way you turned. Aristotle would later call him the inventor of dialectic, the art of argument through contradiction. Whether Zeno actually invented it or just perfected it is debatable, but his approach was revolutionary. He took the tools of logic and sharpened them into weapons. The goal wasn't to convince you that Parmenides was right. The goal was to prove that you were wrong, that your common sense beliefs about reality led to impossible conclusions. If your philosophy contradicted itself, maybe you should reconsider it. Maybe Parmenides had a point. Zeno wrote one book. Just one, probably sometime in the 460s BC when he was still young. We don't have it. Not a single complete copy survived. Everything we know about his arguments comes second-hand, filtered through other philosophers who quoted him, responded to him, or tried to refute him. Plato mentions the book in his dialogue Parmenides, describing how it was stolen from Zeno and published without his permission, which, if true, means Zeno accidentally became famous. The book apparently contained 40 paradoxes about the continuum, 40 different arguments showing why plurality and motion led to contradictions. Most are lost. We have maybe 4 or 5 described in enough detail to reconstruct them. That's it. That's what remains of a work that would influence mathematics and philosophy for 2 millennia. The paradoxes fell into 2 categories: arguments against plurality and arguments against motion. The plurality arguments tried to show that if multiple things exist, contradictions arise immediately. Take any object and ask yourself, can it be divided? If yes, you can keep dividing it forever, which means it's made of infinite parts, which means it has infinite size, but it's clearly finite, so that's a contradiction. If no, it can't be divided, then you've reached some smallest possible piece, some indivisible unit. But if this unit has any size at all, it can be divided in half. If it has no size, it's nothing. And infinite nothings added together make nothing, not the finite object you started with. Either way, you lose. The motion paradoxes were even more troubling because motion was so obviously real that denying it seemed like madness. Zeno knew this. He constructed his arguments precisely because motion seemed undeniable. The dichotomy paradox starts simple. To walk across a room, you must first walk halfway, then you must walk half of the remaining distance, then half of what's left after that. You're always covering half the remaining space, which means you never actually complete the journey because there's always another halfway point ahead. An infinite number of halfway points, in fact. How do you complete an infinite number of tasks? You don't. Motion is impossible. Stand up right now and walk across the room. You just did the impossible, according to Zeno. You completed an infinite number of tasks in finite time. The paradox isn't that motion looks impossible. The paradox is that motion happens constantly while also being logically impossible. Something is wrong with either our logic or our perception, and Zeno wasn't betting on perception. The Achilles and the tortoise paradox made the same point more vividly. Give a tortoise a head start in a race against Achilles, the fastest runner in Greek mythology. Achilles will never catch up. Here's why. By the time Achilles reaches where the tortoise started, the tortoise has moved forward. By the time Achilles reaches that new position, the tortoise has moved again. This continues forever. Achilles keeps getting closer, but never actually catches the tortoise because there's always a gap, however small, and the tortoise fills that gap before Achilles can close it. The gap shrinks towards zero, but never reaches it. Watch a race between a human and a tortoise. The human wins immediately, but Zeno's argument says this shouldn't be possible. The logic seems sound. The conclusion is absurd. That's the trap. You're stuck choosing between logic and observation, between what must be true and what obviously is true. Zeno was fine with this. His job wasn't to resolve the paradox. His job was to create it, to show that your comfortable assumptions about reality fell apart under examination. The arrow paradox approached motion from a different angle. An arrow in flight at any single instant occupies a specific location in space. At that instant, it's not moving because an instant has no duration. No time passes, so no motion happens. But the arrow's flight is made up entirely of these instants. If it's motionless at every instant, when does motion happen? Where does motion come from? You can't build motion out of motionless moments, any more than you can build a journey out of stationary positions. Yet arrows fly. Constantly. These weren't just clever word games. Zeno was exposing something genuinely strange about how we think about space, time, and infinity. The Greeks didn't have calculus, they didn't have modern mathematics. They had geometry and logic and observation. When those tools led to contradictions, they couldn't just calculate their way out. They had to think harder about what the contradictions meant, what they revealed about the structure of reality. Zeno forced that thinking, whether people wanted it or not. The response to his paradoxes tells you everything about how unsettling they were. Aristotle took them seriously enough to write about them extensively. Though he called them fallacies, he tried to refute them by distinguishing between potential infinity and actual infinity. You don't need to complete an infinite number of tasks to cross the room, Aristotle argued. You just need to complete a task that can be divided infinitely, which is different. The distance exists as a whole. The divisions are potential, not actual. This satisfied some people. It didn't solve the paradox so much as reframe it, but reframing sometimes counts as progress. Plato had a different reaction. He thought Zeno was being deliberately provocative, that even Zeno didn't take his own arguments seriously. They were rhetorical exercises, demonstrations of logical technique, not genuine attempts to understand reality. Plato might have been wrong about this. The evidence suggests Zeno believed his arguments revealed real problems with pluralism and motion, real contradictions that couldn't be dismissed as mere wordplay. But Plato's dismissal stuck. For centuries, many philosophers treated Zeno as a sophist, someone who argued for the sake of arguing, who cared more about winning debates than discovering truth. That reputation would eventually reverse. 2,000 years later, mathematicians developing calculus and set theory realized Zeno had been onto something profound. His paradoxes weren't sophistry. They were early glimpses of problems that would require entirely new mathematical frameworks to address properly. The concept of limits, the understanding of infinity as something that could be worked with mathematically rather than just philosophically. The recognition that infinite series could converge to finite values, all of this emerged partly from wrestling with questions Zeno had posed in the 5th century BC. Bertrand Russell put it clearly. After 2,000 years of refutation, Zeno's sophisms were reinstated and made the foundation of a mathematical renaissance. That's not because Zeno was right in any simple sense. His conclusions were wrong. Motion happens, plurality exists. But his arguments revealed deep conceptual problems that couldn't be solved by just asserting the obvious. They required new ways of thinking about continuity, infinity, and the relationship between mathematics and physical reality. But we're getting ahead of ourselves. In the 460s BC, Zeno was a young man in Elea, writing a book that would be stolen and published, that would make him famous in Athens, that would provoke responses from the greatest philosophers of the ancient world. He didn't know any of this yet. He was just trying to defend his teacher's strange philosophy, using logic as a weapon against common sense. The fact that this weapon would still be sharp 2 millennia later, that it would help birth modern mathematics, that it would never quite be defeated or fully understood, none of that was predictable. What happened next in Zeno's life is murkier. The sources conflict, the timeline gets fuzzy, and we're left piecing together fragments. But at some point, probably around 450 BC, Zeno left Elea. He went to Athens with Parmenides, carrying his book, ready to meet the philosophers who would become his critics and eventually his immortalizers. Athens in 450 BC was nothing like Elea. The city sprawled across hills and valleys, dominated by the Acropolis, with its gleaming temples still under construction. The Parthenon wouldn't be finished for another decade, but already the city radiated power and confidence. This was the center of the Greek world, where democracy was being invented, where art and philosophy flourished in ways no other city could match. Zeno and Parmenides arrived as foreigners, outsiders from a distant colony in Italy. But they weren't nobodies. Parmenides had a reputation that preceded him. His poem about the nature of being had circulated among intellectuals. People knew his arguments, even if they disagreed with them. And Zeno's book, the one that had been stolen and published, had made its way to Athens before he did. Plato gives us our only detailed account of this visit in his dialogue Parmenides. Whether the encounter he describes actually happened is questionable. Plato was writing decades later, creating a dramatic philosophical conversation that served his own purposes. He needed Socrates to interact with the great thinkers of the previous generation, so he staged a meeting that might never have occurred. But let's take it at face value for a moment, because the scene Plato paints is too good to dismiss entirely. He describes Parmenides as an old man, around 65, with distinguished white hair. Zeno is about 40, tall and handsome. They're staying with someone named Pythagoras, and young Socrates, maybe 20 years old, comes to visit along with Aristotle, who would later become one of the 30 tyrants. The gathering has the feel of a philosophical salon. Zeno reads from his book, defending his teacher's monism by attacking the coherence of plurality. Someone asks him to read a particular argument again. The discussion begins. What's striking in Plato's account is that Socrates, usually portrayed as the wisest man in Athens, comes across as a talented but inexperienced young philosopher. He challenges Zeno's arguments, but Zeno and Parmenides handle him easily. They're patient with him, almost indulgent, the old masters educating the upstart. Socrates makes a point about forms and participation that would later become central to Plato's philosophy. But in this dialogue, Parmenides systematically dismantles it. The young Socrates is left stammering, realizing he hasn't thought through the implications of his own position. It's a rare moment in Platonic literature where Socrates loses an argument. This might be Plato's invention, a way of showing that even Socrates learned from others, that philosophy is a cumulative enterprise, or it might preserve something real about the encounter. We'll never know for certain. What we do know is that Zeno's arguments made an impression in Athens. They were discussed, debated, attacked. The paradoxes became famous, which means they became problems that needed solving. Every philosopher who came after had to deal with them in some way. But here's what's interesting. Despite the fame, despite the recognition, we don't have evidence that Zeno wrote anything else. The one book composed in his youth apparently satisfied him. He wasn't building a philosophical system or founding a school. He'd made his point. The paradoxes existed. Let others wrestle with them. This is unusual for a philosopher. Most ancient thinkers who gained recognition kept writing, kept developing their ideas. Zeno seems to have stopped. Maybe he felt he'd said what needed saying. Maybe he lost interest. Maybe there were practical reasons we don't know about. The timeline gets fuzzy after the Athens visit. We don't know how long Zeno stayed or when he returned to Elea. We don't know if he made other trips or remained in southern Italy. The sources go quiet on his activities for years. Then the story picks up again with his death, and the death is dramatic enough to have generated multiple conflicting accounts. This is usually a sign that nobody really knew what happened, and people filled the gaps with legend. The most common version comes from Diogenes Laertius, writing in the 3rd century AD, 700 years after the fact. According to Diogenes, Zeno was involved in a plot to overthrow Nercus, the tyrant of Elea. The plot was discovered. Zeno was arrested and tortured to reveal the names of his co-conspirators. He refused. Instead, he asked to whisper the names privately to Nercus. When the tyrant leaned close, Zeno bit his ear and wouldn't let go until he was stabbed to death. It's a good story. It fits the ancient ideal of the philosopher who values truth and loyalty above life. But the details vary wildly across sources. Some say Zeno bit off his own tongue and spit it at the tyrant. Others say he bit the tyrant's nose instead of his ear. One account has him revealing the names of the tyrant's own friends as conspirators, turning the torture session into revenge. The variations suggest embellishment. The core might be true. Zeno probably did die around 430 BC, probably in Elea, possibly in circumstances related to political resistance, but the specific details have been lost to time and replaced with the kind of heroic narrative that ancient writers loved. What matters more than the exact circumstances is what the story reveals about how Zeno was remembered. He wasn't just a clever arguer or a defender of his teacher's strange philosophy. He was seen as someone of principle, someone willing to die rather than betray his commitments. This fits with what we know about Eleatic philosophy more broadly. Parmenides and his followers weren't just playing intellectual games. They believed their arguments revealed truths about reality that contradicted common sense, but were logically necessary. That kind of commitment, the willingness to follow logic wherever it leads, even when it leads somewhere absurd, requires a certain temperament. Zeno had that temperament. His paradoxes weren't attempts to confuse or to show off his cleverness, though they certainly demonstrated cleverness. They were serious arguments meant to establish serious conclusions. The fact that the conclusions seemed impossible didn't make them wrong. It made common sense suspect. This is worth sitting with for a moment. Imagine being so committed to logical reasoning that you're willing to argue motion is impossible while watching people walk past you. That's not insanity. It's a specific kind of philosophical courage, the courage to trust the argument over the evidence of your senses. The Eleatics believed that the senses deceive. What appears to be many things is actually one thing. What appears to move is actually still. What appears to change is actually eternal. These conclusions followed logically from their premises about being and non-being. The fact that reality seemed to contradict them just showed that reality, as we experience it, is illusory. This was radical. Most Greek philosophers tried to explain the world as it appeared, to account for change and motion and plurality. The Eleatic said the world as it appeared was a lie. Only being exists. Being is one, eternal, unchanging, indivisible. Everything else is confusion. Zeno's paradoxes were weapons in defense of this position. If you think motion is real, explain how it's possible given these logical problems. If you think plurality exists, explain how multiple things can be without contradiction. The burden of proof shifted. It wasn't Parmenides who needed to explain why motion seemed to happen despite being impossible. It was everyone else who needed to explain how motion could be possible given the paradoxes. This argumentative strategy was new. Earlier philosophers had presented their views about nature without extensive logical justification. Thales said everything is water. Anaximander said it's the boundless. Heraclitus said it's fire and constant change. These were assertions based on observation and intuition, not deductive arguments from premises to conclusions. Zeno changed the game. He showed that philosophy could be argumentative, that you could use logic as a tool to defend positions and attack opponents. Aristotle later called him the inventor of dialectic, and while that's probably an overstatement, there's something to it. Zeno pioneered a way of doing philosophy that would become standard. The paradoxes themselves fall into two broad categories. The first group attacks plurality, the idea that many things exist. The second attacks motion. We've already looked at some of the motion paradoxes in detail. The plurality arguments are less famous but equally clever. One goes like this: if many things exist, they must be both finite and infinite in number. They're finite because they're exactly as many as they are, no more and no less. But they're also infinite because between any two things, there must be another thing separating them. And between that thing and the others must be more things, and so on without end. Therefore, plurality is contradictory. Another: if many things exist, each thing must be both infinitely large and so small as to have no size. It must be infinitely large because it has parts, and each part has parts, and division can continue without end. So the sum would be infinite, but it must also have no size because if it's made of ultimate parts that have no size, the sum of no sizes is still no size. These arguments have the same structure as the motion paradoxes. They take a common sense belief, in this case that multiple distinct objects exist, and show it leads to contradictions. The conclusion is supposed to be that the common sense belief is false. Modern readers often find the plurality arguments less compelling than the motion ones. They seem to rely on assumptions about infinite divisibility that we can question, but they were taken seriously in antiquity, particularly by the atomists. Leucippus and Democritus, who developed atomic theory in the generation after Zeno, were explicitly responding to Eleatic arguments. They agreed that infinite division was problematic. Their solution was to deny that division could continue infinitely. Eventually you reach atoms, indivisible particles that can't be split further. Problem solved, except the Eleatics could respond, why can't atoms be divided? If they have size, they have parts. If they have parts, they can be divided. Saying they're indivisible is just asserting what you need to prove. This back and forth continued for centuries. The atomists refined their position. The Eleatics refined their objections. Neither side won decisively. The debate forced both to sharpen their arguments, to think more carefully about concepts like divisibility, extension, and composition. That's what Zeno's paradoxes accomplished. They created productive problems, puzzles that couldn't be easily dismissed, but also couldn't be easily solved. They forced philosophers to get more rigorous, to think harder about basic concepts they'd taken for granted. The motion paradoxes had a similar effect. They forced careful thinking about time, distance, infinity, and the relationship between mathematical abstraction and physical reality. They revealed that these concepts were more complicated than they seemed. Consider the arrow paradox again. At any instant, the arrow occupies a space exactly equal to itself. It's not moving during that instant because an instant has no duration. How then does it ever move? Movement would require being in different places at different instants, but at each individual instant, there's no motion. This seems like word games until you try to refute it. The standard response is that motion is a property of the arrow across time, not at an instant. But that just pushes the problem back. How do we define motion across time, except as a series of positions at instants? And if there's no motion at any individual instant, how does stringing instants together create motion? You need a mathematical framework that can handle instantaneous rates of change. You need calculus, but calculus wouldn't be invented for another 2,000 years. In the meantime, the paradox stood as a genuine puzzle. Zeno couldn't have anticipated this. He was making arguments against motion as part of defending Parmenides. He wasn't trying to lay groundwork for future mathematics, but that's what happened anyway. The paradoxes posed questions that would eventually require new mathematical concepts to answer properly. This is why Bertrand Russell praised Zeno so highly. The paradoxes weren't sophistry. They were genuine insights into problems with our basic concepts of space, time, and motion. The fact that ancient Greeks couldn't solve them wasn't a failure of intelligence. It was a lack of the right tools. When those tools were eventually developed, they vindicated Zeno's intuition that something deep and difficult was going on. But we're still in the 5th century BC. Calculus is unimaginably far in the future. Zeno is dead, killed for political resistance or philosophical obstinacy, depending on which story you believe. His book has been stolen and published. His paradoxes are being discussed and debated in Athens and beyond. What happens next is that philosophy moves on. New thinkers emerge with new ideas. Socrates develops his method of questioning. Plato builds his theory of forms. Aristotle systematizes knowledge across every domain. The Eleatic school fades, remembered but not dominant. Zeno becomes a historical figure, someone who posed interesting puzzles that later philosophers reference but don't dwell on. His arguments are treated as challenges that have been more or less adequately answered, even if the answers aren't entirely satisfying. This is how it stood for centuries. Zeno was important but not central, clever but ultimately wrong. His paradoxes were teaching tools, examples of logical reasoning that students studied but weren't expected to take seriously as genuine threats to our understanding of reality. Then something changed. Mathematics evolved. The development of calculus by Newton and Leibniz in the 17th century created new ways of thinking about infinity and continuous change. The formalization of mathematics in the 19th century, particularly work on infinite series and set theory by Cantor and others, provided frameworks for addressing questions Zeno had raised. Suddenly his paradoxes looked different. They weren't just clever puzzles. They were early recognitions of real mathematical difficulties that had taken 2 millennia to properly address. Zeno had been onto something after all. The vindication came slowly, then all at once. For most of history, Zeno's paradoxes were treated like optical illusions. Clever, sure. Interesting to discuss. But ultimately, tricks of language rather than genuine problems. Aristotle had provided what seemed like reasonable responses back in the 4th century BC. He distinguished between potential and actual infinity. Sure, you can potentially divide a distance infinitely, but you don't actually have to complete an infinite number of tasks. Motion happens in finite time. Problem solved. Except it wasn't solved. Aristotle had sidestepped the issue rather than addressing it head-on. His distinction between potential and actual infinity was philosophically convenient but mathematically vague. What does it mean for a division to be potential but not actual? If the divisions exist in any meaningful sense, you still have the problem of infinite subdivision. If they don't exist, what are we even talking about? Medieval philosophers revisited these questions occasionally. Islamic scholars in particular spent time on Zeno, but the paradoxes remained curiosities. The real work of philosophy was happening elsewhere. Theology, logic, metaphysics. Zeno's puzzles about motion and plurality were sideshows. Then the scientific revolution arrived. Galileo started asking questions about how objects actually move, not just whether they move, which seemed obvious from observation, but what motion is mathematically. He discovered that falling objects accelerate at a constant rate. He developed equations to describe projectile motion. He was trying to make motion calculable, predictable, subject to mathematical law. This required thinking carefully about instantaneous velocity. How fast is something moving at a particular moment? Not over an interval, but right now. This is exactly the kind of question Zeno's arrow paradox raises. If an instant has no duration, how can there be motion during it? Galileo didn't solve the paradox, but his work made it urgent. You couldn't do physics without addressing instantaneous rates of change. Newton and Leibniz invented calculus independently in the late 17th century. They were trying to solve practical problems: planetary motion, areas under curves, rates of change. The mathematics worked brilliantly. You could calculate things that had been impossible before, but the foundations were shaky. Calculus deals with infinitesimals, quantities that are infinitely small but not quite zero. When you calculate the slope of a curve at a point, you're looking at the ratio of infinitesimal changes. When you calculate an area under a curve, you're summing infinitely many infinitesimal rectangles. This works. The results match observations. But what exactly is an infinitesimal? Newton called them fluxions and tried to explain them through motion. Leibniz had his own terminology. Neither explanation was entirely satisfactory. Bishop Berkeley, the philosopher, attacked the foundations of calculus in 1734. He called infinitesimals the ghosts of departed quantities and pointed out that the reasoning involved seemed suspiciously like the kind of logical sleight of hand that Zeno had exposed 2,000 years earlier. You want to divide by a tiny quantity to find a ratio, then set that quantity to zero to find the instantaneous rate. But you can't have it both ways. Either the quantity is zero and you're dividing by zero, which is undefined, or it's not zero and you're not actually finding the instantaneous rate. The math worked, but the logic was questionable. For over a century, calculus advanced on shaky foundations. Mathematicians used it because it produced correct results. Engineers applied it to build bridges and predict trajectories. But the theoretical justification remained murky. People were doing mathematics that worked while not fully understanding why it worked. The 19th century brought rigor. Augustin Louis Cauchy developed the theory of limits. Instead of talking about infinitesimals, you could talk about getting arbitrarily close to a value. The limit of a function, as x approaches some value, is what the function approaches, even if it never quite gets there. This avoided the need for infinitesimals while preserving the computational power of calculus. Carl Weierstrass refined this further with his epsilon-delta definition of limits. Suddenly calculus had a firm logical foundation. You could prove theorems rather than just computing results. The subject became rigorous. And here's the crucial point. The framework that made calculus rigorous was addressing exactly the problem Zeno had identified. How do you handle infinite processes? How do you talk about instantaneous rates when instants have no duration? The answers required sophisticated mathematical machinery that took 2 millennia to develop. Georg Cantor's work on infinite sets in the late 19th century added another dimension. Cantor proved that not all infinities are equal. The infinity of counting numbers is smaller than the infinity of real numbers. This sounds absurd, but Cantor made it mathematically precise. You could compare infinite sets, reason about them, prove things about their properties. This connected directly to Zeno's paradoxes. When you divide a distance infinitely many times, you get infinitely many pieces. But Cantor's work showed you could actually handle infinite collections mathematically. You could sum an infinite series and get a finite result. The sum of 1/2 plus 1/4 plus 1/8 and so on equals 1. Exactly 1. Not approximately, not in some hand-wavy philosophical sense. Mathematically, precisely, provably 1. This dissolved the dichotomy paradox. Yes, traversing a distance requires completing infinitely many subdivisions, but completing infinitely many tasks isn't automatically impossible if their sum is finite. You walk across the room by completing an infinite series that sums to a finite distance. The mathematics works out. Bertrand Russell saw this clearly. He'd been working on the foundations of mathematics, trying to derive all of math from pure logic. He understood how recent developments in set theory and analysis had vindicated Zeno. In 1903, Russell wrote that Zeno's arguments, far from being sophisms, were immeasurably subtle and profound. After 2,000 years of refutation, they'd been reinstated as the foundation of a mathematical renaissance. This is remarkable. A philosopher working in the 5th century BC, using only logical reasoning, had identified genuine problems that required advanced mathematics to fully address. Zeno couldn't solve his own paradoxes because the tools didn't exist, but he was right that something deep and difficult was happening with concepts of infinity and continuity. The standard solution using modern mathematics goes like this. Achilles races the tortoise gets a head start. Achilles must first reach where the tortoise started, but by then the tortoise has moved. Achilles reaches that new point. The tortoise has moved again. This continues infinitely. But here's the resolution. Each step takes less time than the previous step. The time intervals form a geometric series that converges to a finite sum. Achilles completes infinitely many steps in finite time. After that finite time, he's past the tortoise. The infinite series sums to a specific moment when Achilles takes the lead. Mathematically, this works perfectly. You can calculate exactly when and where Achilles overtakes the tortoise. The infinite subdivision doesn't prevent the outcome, it describes it. Does this fully resolve the paradox? That depends on what you think the paradox is about. If it's a mathematical question about whether infinite processes can have finite results, yes, it's resolved. Modern analysis handles this cleanly, but if it's a philosophical question about the nature of motion and infinity, some philosophers argue it remains open. The mathematical solution shows that the infinite subdivision is compatible with motion. It doesn't necessarily explain motion. You can calculate where Achilles will be at any time. You can prove he overtakes the tortoise. But does this tell us what motion is, or just how to describe it? This is where the debate gets interesting. Physics uses mathematics to model reality. The models work extraordinarily well. Quantum mechanics, relativity, all of modern physics depends on sophisticated mathematical frameworks. But there's always a question of whether the math describes reality or just predicts observations. Zeno's paradoxes touch on this directly. The arrow paradox asks what happens at an instant. Modern physics sidesteps this by treating motion as a property of objects across intervals. We don't ask what's happening at an instant. We calculate positions and velocities as functions of time. The math works, but it doesn't answer the original question in the way Zeno posed it. Some physicists and philosophers argue this is fine. The question, as Zeno posed it, was confused. Motion isn't something that happens at instants. It's a relationship between positions at different times. Asking about motion at a single instant is like asking about the colour of justice. The question doesn't make sense. Others maintain that this dodges something important. Our experiences of motion happening now, in the present. Physics treats time as a dimension like space, but our experience isn't four-dimensional. We experience a moving present moment. How does that work if motion is just a relationship between different times? Quantum mechanics adds another wrinkle. At quantum scales, particles don't have definite positions until measured. The arrow paradox assumes the arrow occupies a specific place at each instant. Quantum mechanics suggests this assumption breaks down. Particles exist in superposition, spread across multiple possible locations until observation collapses the wave function. Does this resolve Zeno's paradox or deepen it? You could argue that quantum mechanics shows Zeno was right to be skeptical of our intuitive notions of objects occupying definite places. The arrow doesn't have a precise location at each instant, so the paradox's assumption is wrong and there's no paradox. Or you could argue that quantum mechanics makes things weirder. Now we have motion, but the objects moving don't have definite positions. That's not solving the paradox. That's replacing it with something even more paradoxical. Special relativity contributes its own complications. Whether two events are simultaneous depends on your reference frame. There's no absolute present moment. Time itself is relative to motion. An arrow in flight experiences time differently than a stationary observer. What does an instant even mean in this context? These modern developments don't invalidate Zeno's paradoxes. They show how deep the problems go. Zeno identified issues with our basic concepts of space, time, and motion. 2,000 years of mathematics and physics have refined those concepts enormously. We can calculate things Zeno couldn't have imagined. But the fundamental questions he raised about infinity, continuity, and the nature of change remain live issues in physics and philosophy. The paradoxes against plurality are less discussed than the motion paradoxes, but they're equally interesting. Zeno argued that if multiple things exist, they must be both finite and infinite in number. They must be finite because they're exactly as many as they are, but they must be infinite because between any two things, there must be another thing separating them, and between that thing and the original things, more separating things, ad infinitum. This argument seems less compelling than the motion paradoxes. You can just deny the premise that things must be separated by other things, but substitute points on a line for things, and the argument becomes more troubling. Between any 2 points on a line, there's another point. The line contains infinitely many points, but a line segment has a finite length. How do infinitely many points add up to finite distance? This is the same basic problem as the dichotomy paradox, approached from a different angle. Modern mathematics handles it with measure theory and the real number system. Points have zero length. Infinitely many zeros can sum to positive length through the magic of uncountable infinity. The mathematics is rigorous and works perfectly, but does it explain anything? Or does it just formalize the mystery? You've replaced the question, how can infinite things make finite length, with how can uncountably infinite zero-length points make positive length? The mathematical framework lets you calculate with confidence. Whether it provides understanding depends on your philosophy of mathematics. Zeno's method was reductio ad absurdum. Assume the opposite of what you want to prove, show it leads to contradiction, conclude the opposite is true. This is now a standard proof technique. Every mathematics student learns it, but Zeno pioneered it in philosophy. He took ideas his opponents held, showed they led to absurd conclusions, and claimed victory. The problem is that his opponents could play the same game. Assume motion is impossible. But I just walked across the room. That's absurd, therefore motion is possible. Both sides are using reductio ad absurdum. Both generate contradictions. Who wins? This is why the paradoxes were so effective. They weren't just arguments, they were traps. Any response seemed to lead to problems. Deny that motion involves infinite subdivision? Then how do you account for continuity? Accept infinite subdivision? Then how does motion happen? You're stuck either way. The escape route required developing entirely new concepts. You had to build a mathematical framework where infinite processes could complete in finite time, where zero-length points could compose positive-length lines, where instantaneous velocities made sense. This took 2,000 years and the combined efforts of the greatest mathematical minds in history. That's what Russell meant when he said Zeno's arguments were reinstated after millennia of refutation. The early refutations were superficial. They sidestepped the real issues. Only when mathematics became sophisticated enough to directly address the problems Zeno identified could anyone claim to have actually solved them. And even then, the solution is mathematical rather than metaphysical. We can calculate with infinity now. We can prove theorems about infinite series and uncountable sets. We can model motion mathematically with precision. But have we explained what infinity is? What continuity is? What motion is? Maybe those aren't the right questions. Maybe asking for explanations beyond mathematical descriptions is asking for too much. This is a live debate in philosophy of mathematics and philosophy of science. Are mathematical models descriptions of reality or just predictive tools? When we say the real numbers model the continuum, are we discovering something about reality or inventing a useful fiction? Zeno couldn't have anticipated any of this. He was defending his teacher's strange doctrine that reality is one unchanging whole. He created paradoxes to embarrass opponents who believed in plurality and motion. The paradoxes worked too well. They revealed genuine problems that would haunt mathematics and philosophy for millennia. That's the irony of Zeno's legacy. He created these paradoxes to defend Parmenides, to prove that motion and plurality were illusions. Instead, he sparked a mathematical revolution that gave us the tools to describe motion with incredible precision. He wanted to show reality was static and unchanging. He ended up revealing just how complex and subtle change actually is. The historical Zeno is almost invisible to us now. We have none of his original writings. Everything comes filtered through later authors who had their own agendas. Plato portrays him in the dialogue Parmenides, where a young Socrates meets the older philosophers. But scholars debate whether this meeting ever actually happened, or if Plato invented it for dramatic effect. What we do know comes from fragments and second-hand reports. Zeno was from Elea, a Greek colony in southern Italy. He was born around 490 BC. He studied with Parmenides and became his most devoted defender. The two travelled to Athens together when Zeno was around 40 years old. His book of paradoxes was already famous by then. Plato suggests there was a romantic relationship between Parmenides and Zeno. This wouldn't have been scandalous by Greek standards. Older men mentoring younger men often involved romantic elements. Whether true or not, it shows how closely associated the two were in ancient minds. Zeno wasn't just Parmenides' student. He was his protege, his defender, his champion. The paradoxes were meant as weapons in philosophical combat. Parmenides had argued that reality is one unchanging whole. His opponents mocked this. Common sense says we see many things, and they move and change. Parmenides must be crazy or stupid. Zeno struck back. Fine, you believe in plurality and motion. Let me show you the absurdities that follow from your beliefs. You think there are many things, then each thing must be both finite and infinite. You think things move, then Achilles can never catch a tortoise. Your common sense leads to contradictions worse than anything Parmenides claimed. It was brilliant strategy. Instead of defending Parmenides directly, attack the alternatives. Show that the obvious view is actually incoherent. Force your opponents to either accept Parmenides or live with contradictions. Did Zeno actually believe motion was impossible? Probably not in any simple sense. He could see people walking around. He wasn't delusional, but he believed that philosophical analysis revealed problems with our naive understanding of motion. The appearances deceive us. Reality underneath is different from what we observe. This distinction between appearance and reality runs through Greek philosophy. Plato would later develop it into his theory of forms. What we see are mere shadows of true reality. Zeno was making a similar move, though his conclusions differed from Plato's. The paradoxes weren't meant to convince through positive argument. They were meant to create aporia, a state of puzzlement where you can't see your way forward. Your beliefs lead to contradiction. You must abandon something you thought was obvious. But what? And how do you rebuild? This technique became central to philosophy. Socrates would use it constantly, questioning people until they contradicted themselves. The goal wasn't to provide answers, but to show that the obvious answers don't work. Wisdom begins with recognizing your ignorance. Zeno pioneered this approach. Before him, philosophers mostly presented their own positive views about reality. Thales said everything is water. Heraclitus said everything is fire. Pythagoras said everything is number. These were bold claims, but they weren't arguments in our sense. Zeno changed the game. He constructed explicit arguments with premises and conclusions. He showed how accepting certain premises forces you to accept certain conclusions. He turned philosophy into a discipline where you had to defend your views against attack. Aristotle called him the inventor of dialectic. That's the method of argument through question and answer, through examining implications and contradictions. It became the core method of ancient philosophy. Plato's dialogues showcase it constantly. Medieval scholastics perfected it into elaborate disputations. Modern philosophy still uses it, though the style has changed. All this from a man defending a view almost nobody accepts. Parmenides' strict monism, the idea that only one thing exists and nothing changes, found few followers. Even Plato rejected it. Yet Zeno's defense of it created tools everyone used. His death, like much of his life, comes to us through uncertain reports. The most dramatic version says he participated in a plot against the tyrant Zeno of Elea. When captured, he refused to name his co-conspirators. Instead, he asked to whisper the names to the tyrant privately. When Zeno leaned in, Zeno bit his ear and wouldn't let go until guards killed him. It's a great story. Defiant philosopher dying to protect his friends. But is it true? We can't know. Other versions say he bit off his own tongue and spat it at the tyrant, or that he named the tyrant's own friends as conspirators, getting them killed too, or that none of this happened and he died peacefully. What matters is that ancient writers portrayed him as a man of principle, willing to die for his beliefs. Whether the specific details are accurate, this image shaped how later generations understood him. Not just a clever arguer, but someone who put his life on the line for what he thought was right. The paradoxes survived him. They were too interesting, too challenging to forget. Every generation of philosophers had to grapple with them. Some dismissed them as sophistry. Others saw them as genuine problems requiring serious solutions. Aristotle took them seriously, but thought he could refute them. His key move was distinguishing between potential and actual infinity. The divisions in space are potentially infinite, meaning you can always divide further. But they're not actually infinite, meaning there's no completed infinite collection. This let Aristotle say that motion involves passing through potentially infinite divisions without requiring completion of an actually infinite task. You don't have to perform infinitely many actions. You perform one action, moving from start to finish, which potentially contains infinite subdivisions. Does this work? It depends on what you mean by work. Aristotle's distinction is genuine and important. Potential and actual infinity are different, but does the distinction really solve the paradox? You still have to pass through all those points, potentially infinite or not. How does that happen? Medieval philosophers debated Zeno endlessly. They had inherited both Aristotle's physics and Christian theology, which added new wrinkles. God is eternal and unchanging. Does that make reality ultimately static like Parmenides claimed? Or does God create a world that genuinely changes? Thomas Aquinas and others tried to reconcile Aristotle with Christianity. They used Aristotle's potential-actual distinction, but modified it to fit theological needs. God actualizes potentials. Motion is the actualization of potential being. The paradoxes get absorbed into this larger framework. But the framework didn't really solve the paradoxes. It provided a vocabulary for discussing them. You could talk about potentiality and actuality, about substance and accident, about matter and form. This let you say sophisticated things about motion and change. Whether you'd addressed Zeno's core challenges remained debatable. Then came the scientific revolution. Galileo, Descartes, Newton. They needed a new mathematics of motion to describe falling bodies, planetary orbits, projectiles. The old Aristotelian framework wasn't up to the task. Newton and Leibniz independently developed calculus. This was the tool that finally seemed to handle infinite processes rigorously. You could talk about instantaneous velocities, about infinite series converging to finite sums, about continuous change described by differential equations. The mathematics worked spectacularly. Classical mechanics predicted planetary motions to incredible precision. Engineers used calculus to design machines and structures. The success was undeniable, but the foundations were shaky. What exactly is an instantaneous velocity? What does it mean for a series to converge? Newton talked about fluents and fluxions without defining them precisely. Leibniz used infinitesimals that were somehow greater than zero but smaller than any finite quantity. Bishop Berkeley attacked this in his 1734 essay, The Analyst. He called infinitesimals the ghosts of departed quantities. How can you base rigorous mathematics on concepts you can't define coherently? The calculus works in practice, but makes no sense in theory. This criticism stung because it was valid. The early calculus was effective, but logically unclear. It took another century to fix the foundations. In the 1800s, mathematicians like Cauchy and Weierstrass rebuilt calculus using the concept of limits. Instead of infinitesimals, you have limits. The derivative isn't the ratio of infinitely small quantities, it's the limit of ratios as quantities approach zero. The integral isn't a sum of infinitely many infinitesimal areas. It's the limit of finite sums as subdivisions get finer. This approach is rigorous. You can prove theorems, avoid contradictions, build a solid foundation. It's what every calculus student learns today, though usually without appreciating the historical struggle behind it. Did this finally answer Zeno? In a sense, you can now rigorously describe how infinite subdivisions work. You can prove that infinite series can sum to finite values. You can define instantaneous velocity without paradox. But notice what happened. Mathematics developed tools to work with infinity. It didn't explain what infinity is. The limit concept lets you avoid talking about infinitely many things existing simultaneously. You talk about what happens as processes continue indefinitely. Is that the same as completing an infinite process? Philosophers still argue about this. The mathematics is clear, and works. The metaphysics remains murky. Then in the late 1800s came set theory. Georg Cantor showed that you could rigorously treat infinity as a completed whole. There are infinite sets. You can compare their sizes. You can prove theorems about them. This was revolutionary and controversial. Many mathematicians resisted. Infinity had always been potential, a process without end. Cantor said no, infinity can be actual. There are infinite collections that exist as completed wholes. He even showed there are different sizes of infinity. The natural numbers form an infinite set. The real numbers form a larger infinite set. You can prove this rigorously using his diagonal argument. This framework handles Zeno's paradoxes directly. A line segment contains uncountably infinitely many points. That's fine. Uncountable infinity is a legitimate mathematical concept. Motion involves passing through uncountably many positions. No problem. The mathematics handles it. But again, does this explain anything? Or just formalize the mystery? You've proven that infinite sets can exist mathematically. Does that mean they exist physically? Does it tell us what motion actually is? Different philosophers give different answers. Platonists say mathematical objects exist independently of the physical world. The infinite sets are real in their own realm. Motion participates in these mathematical structures. Nominalists say mathematical objects are just useful fictions. The sets don't really exist. They're tools we use to organize our thinking. Motion is real, but the mathematical description is just our way of modeling it. Empiricists say we should stick to what we can observe and measure. The mathematics predicts observations accurately. That's all we need. Questions about what infinity really is go beyond science into metaphysics. Each view has strengths and weaknesses. None is obviously correct. 2,000 years after Zeno, we're still arguing about the fundamental issues he raised. Modern physics adds new twists. Quantum mechanics suggests space and time might not be infinitely divisible. At the Planck scale, roughly 10 to the power of minus 35 meters and 10 to the power of minus 43 seconds, quantum effects dominate. Below these scales, our usual concepts of space and time may break down. Some physicists speculate that space-time is fundamentally discrete, like pixels on a screen. If so, Zeno's paradoxes might not apply. You can't subdivide indefinitely if there's a smallest possible length. But this is speculative. We don't have a complete theory of quantum gravity. We don't know for sure whether space and time are continuous or discrete at the deepest level. It's an open question in fundamental physics. Relativity adds its own complications. In special relativity, different observers disagree about simultaneity. What's happening now depends on your reference frame. In general relativity, space-time is curved by matter and energy. The geometry itself is dynamic. How do Zeno's paradoxes fare in relativistic space-time? The mathematics handles it, but the conceptual puzzles remain. What does it mean to move through a continuum when the continuum structure depends on your motion? These aren't just abstract questions. They touch on the deepest issues in physics. What is space? What is time? Are they fundamental or emergent? Do they exist independently or only in relation to matter and motion? Zeno couldn't have imagined quantum mechanics or relativity, but his paradoxes forced us to think carefully about space, time, and motion. They showed that our intuitive understanding is incomplete. They demanded precise analysis. That's why they still matter. Not because Zeno was right about motion being impossible, he wasn't, but because he identified genuine problems that required genuine solutions. He showed that obvious things aren't always simple once you examine them closely. The history of responses to Zeno reveals something fascinating. Every era thinks it's finally solved the paradoxes, and every era discovers new depths to the problems. Aristotle thought he'd settled everything. Motion is possible because infinity is potential, not actual. You never complete an infinite series. You just keep going. Problem solved. Except it wasn't, because Aristotle's solution doesn't really address the core issue. Saying infinity is potential rather than actual just relabels the puzzle. It doesn't explain how you traverse a continuum. It doesn't tell us what motion fundamentally is. Medieval philosophers tried different approaches. Some followed Aristotle. Others proposed that space and time are discrete, made of indivisible atoms. If there's a smallest distance, you can't subdivide forever. The paradoxes dissolve, but this creates new problems. If space is made of discrete chunks, what determines their size? Why that size and not another? And how does motion work when you're jumping from one discrete location to the next? The 17th century brought calculus and new optimism. Newton and Leibniz could handle infinite series mathematically. You could sum them, analyze them, use them to describe motion precisely. The mathematics worked beautifully. Physics advanced rapidly. Yet philosophers noticed something odd. The mathematical success didn't eliminate the conceptual puzzle. You could calculate where Achilles catches the tortoise. You couldn't explain what's actually happening when he traverses infinitely many points. George Berkeley, an 18th century philosopher, attacked calculus on exactly these grounds. He called infinitesimals ghosts of departed quantities. How can something be infinitely small but not zero? It's incoherent, he argued. The mathematics might work, but it's based on logical nonsense. Berkeley had a point. The foundations of calculus were shaky for over a century. Mathematicians used infinitesimals successfully, without really understanding what they were or why they worked. It was effective magic. The 19th century brought rigor. Weierstrass reformulated calculus using limits, no more infinitesimals, just ordinary numbers approaching other numbers. Cantor developed set theory, giving infinity a solid mathematical foundation. Dedekind constructed the real numbers rigorously from rational numbers. These developments seemed to vindicate calculus. The mathematics was now on firm ground. You could prove theorems about infinite sets, continuous functions, limits. Everything was precise and rigorous. Does this solve Zeno's paradoxes? Depends on what you mean by solve. Mathematically, yes. We can describe motion through a continuum using rigorous mathematics. We can sum infinite series. We can define what it means for Achilles to traverse infinitely many points. The calculations work. The predictions match observations. Philosophically, that's less clear. Bertrand Russell thought the mathematical progress vindicated Zeno. Not because Zeno was right about motion being impossible, but because Zeno identified real problems that required sophisticated mathematics to address. Russell praised Zeno as a genius ahead of his time. Other philosophers disagree. They argue that mathematical formalism doesn't explain physical reality. Proving that infinite sets can exist mathematically doesn't prove they exist physically. Showing how to sum an infinite series doesn't explain what's happening when you actually move. This gets to a deeper question about the relationship between mathematics and reality. Is mathematics discovered or invented? Does it describe the world or just organize our thoughts about the world? When we use infinite sets to model motion, are we discovering facts about motion or imposing mathematical structures onto physical processes? Platonists say mathematics exists independently. Mathematical objects are real in their own right. Physical reality participates in or approximates these mathematical structures. When we use calculus to describe motion, we're discovering genuine mathematical facts about how motion works. Nominalists say mathematical objects are useful fictions. They don't really exist. They're tools we construct to predict and control our environment. The success of calculus shows it's a useful tool, nothing more. Formalists say mathematics is just symbol manipulation following rules. It doesn't need to refer to anything real. As long as the system is consistent, that's sufficient. Whether it describes reality is a separate question, for empirical science. Each position handles Zeno differently. For Platonists, Zeno's paradoxes reveal genuine features of mathematical reality. Motion really does involve infinitely many points. The continuum is genuinely dense and uncountable. These are facts about the mathematical structure underlying physical space. Understanding the mathematics is understanding motion. For nominalists, Zeno's paradoxes show the danger of taking mathematics too literally. Of course, you can't really complete infinitely many tasks, but that's fine because motion isn't really infinitely divisible. It's continuous, yes, but the infinite subdivision is just a mathematical model, not physical reality. For formalists, the paradoxes are interesting logical puzzles. Mathematics provides consistent frameworks for handling them. Whether those frameworks describe physical motion is beyond mathematics. That's a question for physics. None of these positions is obviously correct. They've been debated for centuries. They'll be debated for centuries more. What's interesting is that Zeno's paradoxes force us to confront these deep issues. They're not just puzzles about motion, they're entry points into fundamental questions about reality, mathematics, and knowledge. Consider what Zeno actually accomplished. He took something everyone experiences daily and showed it's conceptually problematic. Walking across a room seems simple. Zeno demonstrated it's philosophically complex. This is philosophical progress, even if it doesn't feel like it. Philosophy often makes things more complicated before making them clearer. It reveals hidden assumptions and unexamined concepts. Before Zeno, people assumed motion was straightforward. You move from here to there. Simple. Zeno showed it's not simple at all. What does it mean to occupy a position? What does it mean to change positions? How do you get from one state to another? These questions led to profound developments in mathematics, physics, and philosophy. Calculus, set theory, topology, theories of space and time. All of these emerged partly from thinking through the problems Zeno identified. That's the real legacy. Not whether Zeno was right or wrong about motion being impossible, but that he forced serious thought about concepts we'd taken for granted. Modern philosophy of physics continues this tradition. Philosophers examine quantum mechanics, relativity, quantum field theory, looking for conceptual problems and hidden assumptions. They ask what these theories actually tell us about reality, what they mean, not just how to calculate with them. Some physicists dismiss this as pointless. The mathematics works, the predictions match experiments. What more do you want? But history suggests philosophical analysis matters. Conceptual confusion can block scientific progress. Clear thinking about foundations can open new paths. Einstein's work on relativity involved as much philosophy as physics. He had to think carefully about what we mean by simultaneity, about how we measure time and distance. Zeno's contribution was making the familiar strange, showing that obvious things aren't obvious once you examine them closely. This is what good philosophy does. It questions what seems unquestionable. It finds problems in what seems problem-free. Of course, taken too far, this leads nowhere. You can question anything endlessly. You can doubt everything. At some point, you need to accept something and move forward. But Zeno's paradoxes occupy a sweet spot. They're not pointless skepticism. They identify genuine difficulties in our understanding of motion, infinity, and continuity. They demand real solutions, not just dismissal. The solutions that emerged, calculus, set theory, rigorous analysis, weren't ad hoc patches. They were profound developments that transformed mathematics and science. They gave us tools to handle problems far beyond Zeno's original puzzles. That's the mark of a good philosophical problem. It stimulates progress in unexpected directions. It opens up new areas of inquiry. It reveals connections between seemingly separate issues. Zeno connected questions about motion to questions about infinity, about the continuum, about the relationship between mathematics and physical reality. These connections turned out to be enormously fruitful. They're still being explored today in cutting-edge physics and mathematics. Consider quantum field theory. It treats particles as excitations in quantum fields. These fields are defined at every point in space-time. That's an infinite number of points. The mathematics handles this, but the conceptual issues are thorny. What does it mean for a field to have a value at every point when there are uncountably many points? Or consider the problem of renormalization in quantum field theory. Calculations produce infinite results. Physicists use sophisticated techniques to extract finite, physically meaningful predictions. But what's really happening? Are the infinities genuine features of reality, artifacts of our mathematical methods, signs that the theory needs modification? These are Zeno's questions in modern dress. How do we handle infinity in physical theories? What's the relationship between mathematical formalism and physical reality? When can we trust mathematical calculations even when they involve infinite quantities? The fact that these questions persist shows Zeno identified something fundamental, not just a quirk of ancient Greek thought, a genuine tension between our intuitive understanding of motion and the mathematical structures needed to describe it precisely. Here's something remarkable. Zeno had no calculus, no set theory, no advanced mathematics, just pure reasoning about motion and division. And he created problems that still challenge us. That's intellectual power, creating puzzles that remain relevant across 2,500 years, across revolutions in mathematics, physics, and philosophy. The specifics have changed, the core issues haven't. We now know more about infinity than Zeno could have imagined. We have rigorous mathematics, experimental physics, sophisticated theories, yet we're still arguing about whether motion involves completing infinitely many tasks, whether the continuum is a useful model or accurate description, whether mathematical infinity corresponds to physical infinity. Part of this is inevitable. Philosophy asks questions that can't be settled definitively. Questions about what exists, what we can know, what concepts really mean. These admit multiple reasonable answers. Progress happens through clarification, not final resolution. But part of it is specific to Zeno's paradoxes. They touch on concepts that are genuinely difficult. Infinity, continuity, change. These resist simple analysis. Every attempt to understand them completely reveals new subtleties. Maybe that's okay. Maybe some questions are meant to be perpetually open. Not because we're stupid or because they're meaningless, but because they're deep enough that each answer generates new questions. Zeno started a conversation that's still ongoing. That's a kind of immortality most philosophers would envy. The original purpose behind these arguments gets lost sometimes. Zeno wasn't trying to prove motion doesn't exist. He could see runners winning races. He wasn't denying the obvious. What he was doing was defending his teacher Parmenides. Parmenides had this radical idea. Reality is one, unchanging, indivisible. Everything else, all the change and motion we perceive, that's illusion. Common sense screamed that Parmenides was wrong, so critics attacked. They said his monism was absurd, that it contradicted everyday experience. Zeno stepped in. He turned the argument around. You think my teacher's ideas contradict common sense? Fine. Let's examine your common sense. Let's see if your beliefs about plurality and motion are actually coherent. Turns out they're not. Your worldview, the one that seems so obvious, leads to contradictions just as severe as anything in Parmenides. This was defensive philosophy. Zeno was protecting Parmenides by attacking the attackers, showing that if Parmenides' monism is absurd, then so is the pluralist alternative. Maybe both views have problems. Maybe reality is stranger than either side admits. We don't know the full range of Zeno's arguments. According to Proclus, he wrote 40 paradoxes about plurality, 40 different ways to show that believing in many things leads to contradictions. We have fragments of maybe 2 or 3 of these. The rest are lost. Imagine what we're missing. 40 arguments, each one presumably as clever as the motion paradoxes, each one finding a different angle to attack the idea of multiplicity. The ancient world had access to all of them. We're working with scraps. What we do have suggests the pattern. Take the paradox about large and small. If many things exist, Zeno argued, each thing must be both infinitely large and infinitely small. Why? Because anything that exists must have size. If it has no size, it's nothing. But if it has size, it can be divided. The parts have size too, they can be divided. This continues infinitely. So each thing is composed of infinitely many parts. Infinite parts means infinite size. But wait, if you divide something infinitely, you eventually get to parts with no size. Otherwise you could never exhaust it. Parts with no size add up to nothing. So the thing has no size after all. Infinitely large and infinitely small simultaneously. Contradiction? Modern readers might object. We have atoms, fundamental particles. Division stops there. But Zeno was asking a conceptual question, not an empirical one. If things are infinitely divisible in principle, this problem arises. And in mathematics, we do treat objects as infinitely divisible. Lines contain infinitely many points. So Zeno's question remains relevant even after atomic theory. Another argument attacked the very notion of separate objects. If two things are distinct, something must separate them. Either there's a gap between them, or there's not. If there's no gap, they're touching. They're connected. Are they really two things, or one? If there is a gap, what fills it? Empty space? Then that's a third thing. Now you have 3 things instead of 2. What separates the gap from the objects? You need more gaps. This generates an infinite regress. You might say the gap is nothing, but nothing can't separate things. Nothing is absence. It has no properties. It can't do anything. So if nothing separates the objects, they're not really separated. They're one thing again. These arguments feel slippery, like verbal tricks, but they're pointing at genuine conceptual difficulties. What does it mean for objects to be distinct? What are the conditions for individuality? How does space work? These aren't silly questions. They're foundational issues in metaphysics and physics. The motion paradoxes get more attention because they're easier to visualize. Achilles chasing the tortoise creates a clear mental image. The plurality arguments are more abstract, harder to grasp, but they're equally sophisticated, maybe more so. Both types of arguments share a structure. Start with a common assumption, analyze it carefully, show it leads to contradiction. Therefore, the assumption must be false. This is reductio ad absurdum, proof by contradiction. Zeno didn't invent it, but he was among the first to use it systematically. That alone makes him significant. The technique became standard in mathematics. You want to prove something? Assume the opposite. Derive a contradiction. Therefore, your original claim must be true. Mathematicians use this constantly. It's one of the most powerful tools in the kit. Zeno was doing this in the 5th century BC, but he was using it for a strange purpose, not to establish mathematical truths, to undermine physical intuition, to show that our everyday beliefs about reality don't hold up under scrutiny. That's unsettling. It should be. That's the point. Think about what he was attempting. He wanted to shake people's confidence in the obvious, to make them doubt what seemed most certain. Motion happens. Things are separate. These feel like bedrock. Zeno drilled into the bedrock and found it unstable. The Eleatic school didn't last. Parmenides' strict monism was too extreme, too disconnected from experience. But the questions Zeno raised outlived the school. They infected philosophy, made it impossible to take common sense at face value, forced people to justify what they'd previously assumed. This is what good philosophy does. It makes the familiar strange. It asks why. not to be annoying, though it often is annoying, but because examination reveals hidden complexity. What seems simple rarely is. Zeno understood this. His legacy isn't just the specific paradoxes, it's the attitude, the willingness to question everything, the demand for logical rigor, the recognition that intuition can mislead. These became core philosophical values. Socrates would embody them. So would Plato and Aristotle. The entire Western philosophical tradition inherited Zeno's skeptical method. He also influenced science, not directly. He was wrong about motion being impossible, but indirectly, through the mathematical developments his paradoxes stimulated. When Newton and Leibniz invented calculus, they weren't thinking about Zeno, but calculus solves Zeno's problems. It provides tools to handle infinity rigorously, to sum infinite series, to work with instantaneous rates of change. Those tools enabled modern physics, Newton's laws, Maxwell's equations, Einstein's relativity, quantum mechanics. None of this works without calculus, and calculus emerged partly from wrestling with the mathematical issues Zeno identified. The connection is indirect but real. There's another legacy. Zeno showed that pure reason can challenge empirical certainty. You don't need experiments to create problems for science. Logic alone can do it. This is still true. Philosophers of science use logical arguments to critique physical theories, to expose hidden assumptions, to identify conceptual inconsistencies. The relationship between philosophy and science has always been tense. Scientists often view philosophers as irrelevant. Philosophers sometimes think scientists are naive about conceptual foundations. But the dialogue continues. It has to. Because scientific theories make philosophical assumptions about causation, about laws of nature, about what exists. These assumptions need examination. Zeno's paradoxes remain a testing ground. New interpretations appear regularly. Each one claims to finally resolve the paradoxes. Then someone else finds a problem with that resolution, proposes a different approach. The cycle continues. Why can't we settle this? Part of it is that different people mean different things by resolution. Some want mathematical answers. Others want metaphysical ones. Some think the paradoxes are pseudo-problems. Others think they reveal deep truths. There's no consensus on what would count as a satisfactory solution. Part of it is that the paradoxes operate at the intersection of multiple disciplines. Mathematics, physics, philosophy, cognitive science, each field approaches them differently. Mathematicians are satisfied with convergent series. Physicists want empirical predictions. Philosophers demand conceptual clarity. These goals don't always align, and part of it is that Zeno touched something fundamental, something about how we understand change and continuity, about the relationship between discrete and continuous, between finite and infinite. These concepts are genuinely hard. We've made progress. We haven't finished. Consider digital versus analog. Computers process discrete information, bits that are either 0 or 1, nothing in between, but they can simulate continuous processes. Graphics look smooth. Sound seems continuous. Yet underneath, it's all discrete, ones and zeros. Is the continuity real or illusory? This echoes Zeno's concerns. Is motion genuinely continuous? Or is it made up of discrete moments? If it's discrete, how small are the moments? If it's continuous, how do we handle the infinite divisibility? Different answers lead to different physics. Quantum mechanics suggests spacetime might be discrete at the Planck scale. Distances smaller than about 10 to the power of minus 35 meters might not be meaningful. Time intervals shorter than 10 to the power of minus 43 seconds might not exist. If true, this would resolve Zeno's paradoxes in a surprising way. Motion wouldn't involve infinite division because there's a smallest step, but this is speculative. We don't have a complete theory of quantum gravity. We don't know if space-time is fundamentally discrete or continuous. The question remains open. Zeno's question, dressed in modern physics. Then there's the arrow paradox and quantum mechanics. In quantum theory, particles don't have definite positions and velocities simultaneously. Heisenberg's uncertainty principle forbids it. The more precisely you know position, the less precisely you know velocity, and vice versa. This connects to Zeno's insight. At an instant, the arrow has a position. Does it have a velocity? Classically, velocity at an instant is the derivative, the limit of average velocity over smaller and smaller time intervals. But quantum mechanics says this picture breaks down. You can't simultaneously specify position and velocity precisely. Does this vindicate Zeno? Some think so. The arrow paradox anticipated quantum uncertainty. It showed that classical assumptions about motion at an instant lead to problems. Quantum mechanics solved those problems by abandoning the assumptions. Others disagree. Quantum mechanics still allows motion, just not the deterministic motion of classical physics. Particles move in probabilistic ways described by wave functions. Zeno's paradox claimed motion is impossible. Quantum mechanics doesn't say that. It says motion is different from what we thought. These debates get technical fast, but they show something important. Zeno's paradoxes aren't just historical curiosities, they're live issues in foundations of physics. They force us to clarify what we mean by motion, time, continuity. These clarifications matter for how we build physical theories. Beyond physics and mathematics, the paradoxes influence how we think about change in general. Not just physical motion, any kind of transition. How does anything go from one state to another? Take decision-making. You're choosing between options. At each moment, you're in some state, undecided or leaning one way, or committed. How do you transition between these states? Is there a moment when you're exactly balanced, or is the transition gradual with no precise boundary? This isn't just academic, it affects legal questions. When does someone become responsible for a decision? When does consent occur? When does a contract form? These have practical consequences, and they involve conceptual issues similar to Zeno's paradoxes. Or consider identity over time. You change constantly. Cells replace themselves. Memories form and fade. Are you the same person you were 10 years ago? In what sense? There's continuity, but also change. How do you reconcile them? This is the ship of Theseus problem. If you replace every plank, is it the same ship? Most people say yes, but why? None of the original material remains. What preserves identity? The structure? The function? The history? Zeno's paradoxes raise similar questions about continuity and identity. A moving object occupies different positions at different times. Is it the same object? What makes it the same? The continuous path it traces. But we've seen that path is problematic. It involves infinity. It requires completing uncountably many steps. These aren't just philosophical puzzles. They affect how we model the world, how we write laws, how we design systems. The conceptual foundations matter. Zeno forces us to examine them. Let's talk about something stranger. What if the paradoxes aren't actually about motion at all? Some modern interpreters argue Zeno wasn't trying to prove motion is impossible. He was making a different point entirely. He was attacking the assumptions we use to think about reality. The idea that space and time can be divided infinitely. The idea that mathematical descriptions capture physical truth. The idea that our concepts correspond to how things actually are. This reading makes Zeno less of a crank. He's not denying obvious facts. He's questioning the frameworks we use to understand those facts. And that's a legitimate philosophical project, one that continues today. Consider how we build scientific theories. We start with observations, we create mathematical models, we test predictions, but there's always a gap between the math and the reality. The math is exact. Reality is messy. How do we bridge that gap? Physicists make idealizations. Point particles with no size, perfectly rigid bodies, frictionless surfaces. None of these exist, but they're useful. They let us build models that work. Then we add complications, finite size, deformation, friction. We get closer to reality, but we never fully reach it. Zeno's paradoxes highlight this gap. They show that perfect mathematical descriptions lead to strange conclusions, infinite sums, completed infinities, tasks with no first step. These concepts work mathematically. Do they work physically? That's unclear. Philosophy of science struggles with this. What's the relationship between our theories and reality? Are theories true descriptions? Or just useful tools? Instrumentalists say theories don't need to be true. They just need to make accurate predictions. Realists say no. Good theories tell us what the world is actually like. Zeno's paradoxes support the instrumentalist view. They show that literally, true descriptions might be impossible. We can have useful models, we can calculate correct answers, but the underlying reality might resist complete conceptualization. The map isn't the territory. It can't be. This connects to limits of knowledge. Some things might be inherently unknowable, not because we lack information, because our conceptual tools are inadequate. Like trying to capture continuous motion using discrete concepts. The tools don't fit the task. Mathematics faces similar issues. Gödel's incompleteness theorems showed that any sufficiently complex mathematical system contains true statements that can't be proved within that system. There are limits to what formal methods can achieve. Some truths escape formalization. Zeno's paradoxes anticipated this. They showed that intuitive concepts like motion create formal problems, problems that can't be resolved by adding more axioms or being more careful. The problems are baked into the structure of thought itself. Does this mean we should give up on understanding? No. It means we should be humble. Our theories are approximations, useful approximations, but approximations nonetheless. Perfect understanding might be impossible. And that's okay. Science progresses by building better approximations. Newton's mechanics worked for centuries. Then Einstein showed it was approximate, good enough for everyday speeds, but breaking down near light speed. Quantum mechanics added more corrections. General relativity added others. Each theory is more accurate than the last, but none are final. Zeno reminds us of this. Motion seems simple, but analyze it carefully, and paradoxes emerge. We resolve them with calculus, but calculus makes assumptions. Infinitely divisible space. Continuous functions? Are these assumptions true, or just useful? We don't know, maybe we can't know, but we can keep refining our theories, keep testing them, keep finding where they break down. That's how science works, not by reaching final truth, by approaching it asymptotically, getting closer, but never quite there. This philosophical perspective changes how we view Zeno. He's not the enemy of progress. He's a reminder of its limits, a cautionary voice saying, don't mistake your models for reality. Don't assume your concepts capture everything. There's always more mystery beneath the surface. Now let's return to Zeno's life, because there's one part we haven't covered, how he died, and it's a hell of a story. Around 430 BC, Elea was ruled by a tyrant named Nearchus. Tyranny was common in Greek city-states. A strong man seizes power, rules through force, suppresses opposition. This connects to his philosophy. Zeno questioned authority, not just political authority, intellectual authority. The authority of common sense, of intuition, of established wisdom. He demanded justification, proof, argument. That attitude was dangerous. In politics and philosophy both, it threatens people who rely on unquestioned assumptions, who want their power or their ideas accepted without scrutiny. Zeno wouldn't grant that. He'd ask, why? Prove it. Show me it's not contradictory. This made him enemies. intellectual and political. Both kinds of enemies can kill you. Ancient Athens executed Socrates for asking too many questions. Elea tortured Zeno for the same reason. Different questions, same attitude, same result. But the ideas survived. That's what matters. Zeno died around 430 BC. His book was lost, but the paradoxes lived on, transmitted through Plato, through Aristotle, through commentators and critics. Each generation grappled with them. Each generation failed to fully resolve them. 2,400 years later, we're still grappling, still debating, still finding new angles. The paradoxes have generated thousands of pages of analysis, entire academic careers, multiple mathematical frameworks, and we're not done. Why do they persist? What makes them so durable? Part of it is their simplicity. You don't need advanced math to understand the basic problem. Achilles chases the tortoise. At each point, the tortoise has moved. How does Achilles catch up? Everyone gets the puzzle, but solving it requires sophisticated tools. That combination is rare. Most simple questions have simple answers. Most hard questions are complicated to even state. Zeno found questions that are simple to ask, but hard to answer. Those stick around. Another reason is their generality. The paradoxes apply to any motion, any change, any transition. They're not about specific physical situations. They're about the structure of space, time, and continuity itself. Universal questions remain relevant. But there's something deeper. The paradoxes touch on the gap between thought and reality, between our concepts and the world. That gap is permanent. We can narrow it. We can't close it. So the paradoxes will always have bite. Every new framework for understanding motion creates new versions of Zeno's problems. Calculus seemed to solve them. Then people noticed issues with infinitesimals. Non-standard analysis addressed those, but created new questions. Set theory formalized infinity. But which set theory? Different axioms give different answers. Physics keeps encountering Zeno-like issues. Quantum mechanics, relativity, quantum field theory. Each framework handles continuity and infinity differently. Each makes different assumptions about space and time. None are obviously correct. All are useful. This is Zeno's legacy, not a solved problem. An eternal question, a reminder that even our best theories rest on assumptions we can't fully justify. That understanding has limits, that mystery persists. He did this with simple thought experiments. A runner, an arrow, a tortoise, no equipment, no experiments. Just logic, just careful thinking. And he created problems that outlasted empires. Ancient Greece fell, Rome fell. Medieval Christianity rose and declined. The scientific revolution transformed everything. The modern world emerged. Through all of it, Zeno's paradoxes remained relevant. Different solutions, different frameworks, same fundamental puzzle. That's intellectual achievement on a scale that's hard to comprehend. One man? One book? Lost completely. But the ideas? Immortal. Philosophers 2,400 years later are still wrestling with them. Still finding new implications, still discovering connections to modern science. How many thinkers can claim that? How many ideas last 24 centuries and remain vital? Not many. Zeno earned his place. His method matters too. He invented dialectic, the art of argument through contradiction. You take an opponent's assumption, you derive absurd consequences. You force them to either accept the absurdity or reject the assumption. This became central to philosophy. Socrates used it, Plato built on it, medieval scholastics refined it, modern logic formalized it. Reductio ad absurdum is now a standard proof technique in mathematics. Trace it back far enough, you reach Zeno. He showed that you could attack ideas with ideas. That logic was a weapon. That careful reasoning could undermine seemingly solid positions. This was new. Previous philosophers mostly asserted views. Zeno argued. He demanded his opponents argue too. This changed philosophy forever, made it more rigorous, more adversarial, more focused on proof and counterexample. Not everyone likes this development. Some think it made philosophy too technical, too removed from life. Maybe, but it also made philosophy more honest, harder to fool yourself, harder to accept weak arguments. Zeno's paradoxes exemplify this. They're honest, they don't hide difficulties, they expose them. They say, look, here's a problem, a real problem. Your intuitions say motion exists. Your logic says it's impossible. Something's wrong. Figure out what. That honesty is rare. Most people paper over contradictions, ignore problems, hope they'll go away. Zeno did the opposite. He highlighted contradictions, made them impossible to ignore, forced people to confront them. This is philosophy at its best, not providing answers, asking better questions, not resolving all doubts, showing where doubts are justified, not making things simple, revealing complexity that was always there. Zeno didn't solve the paradoxes, he created them. That's his achievement. He showed us problems we didn't know we had. And 2,400 years later, we're still grateful, still learning from them, still finding new depths. That's what great philosophy does. It doesn't age, it doesn't become obsolete, it remains perpetually relevant because it addresses questions that can't be fully answered, only better understood. Zeno understood motion better than anyone before him. Not because he explained it, because he showed what needed explaining. He revealed the mystery beneath the obvious, the paradox within the mundane. We walk across rooms without thinking. Zeno made us think, made us question, made us realize that even the simplest motions involve infinite complexity. That's a gift, a strange gift, but a gift nonetheless. So here's what we're left with. A man who died 2,400 years ago, who wrote one book that's completely lost, who's remembered only through his enemies' descriptions of his arguments. And those arguments, they're still unresolved, still debated, still generating new mathematics and physics and philosophy. That's Zeno of Elea, the man who proved motion is impossible, except it isn't. Or is it? We're still figuring that out. And we probably always will be. 24 centuries. That's how long Zeno's arguments have survived. Not because they were right, they weren't. We cross rooms constantly. Achilles catches the tortoise every time. Motion happens. But Zeno showed it's not simple, not obvious, not easy to explain once you start asking the right questions. He died around 430 BC, probably tortured, possibly defiant, definitely forgotten by most of his contemporaries. The book he wrote disappeared. The Eleatic school faded. Parmenides' strict monism found no followers. But the paradoxes, they kept going. Through Plato, through Aristotle, through every philosopher who thought they'd finally solved them, through mathematicians who discovered they hadn't. Calculus seemed like the answer. Finally we could handle infinite series, sum them, make sense of them. Achilles overtakes the tortoise at exactly this point, at exactly this time. Mathematics proves it, except mathematics had shaky foundations for over a century, infinitesimals that were and weren't zero, limits that approached but never reached. It worked, nobody knew why. Then came Rigor, Weierstrass, Cantor, set theory, real analysis, actual foundations for calculus, proper definitions, provable theorems. The mathematics became solid. Did it solve Zeno? Depends who you ask. Mathematicians say yes. We can describe motion through a continuum rigorously. We can sum infinite series properly. We can define instantaneous velocity without contradiction. The math works. The predictions match reality. Problem solved. Philosophers aren't convinced. Mathematics shows how to calculate. Not what's actually happening. Does motion really involve completing infinitely many steps? Or is that just our model? The map works. Is it the territory? Physicists add complications. Quantum mechanics suggests particles don't have definite positions and velocities simultaneously. Relativity makes simultaneity relative. Quantum field theory treats particles as field excitations at uncountably many points. Each framework handles infinity differently. None obviously capture ultimate reality. Zeno anticipated this. Not the specific theories, the fundamental difficulty. He showed that our intuitive concepts about motion and continuity and change don't hold up under analysis, that something's wrong with how we think about these things. 24 centuries later, we're still working out what. That's the legacy. Not solved problems, permanent questions, reminders that understanding has limits, that our best theories rest on assumptions we can't fully justify, that the obvious isn't always simple once you examine it closely. He changed philosophy forever, made it argumentative, rigorous, focused on finding contradictions in opposing views. Socrates learned from this, so did Plato, so did everyone after. Philosophy became about argument, about proof, about showing where ideas fail. Zeno pioneered that. He changed mathematics too, indirectly. His paradoxes forced development of tools to handle infinity properly. Calculus emerged partly from these problems. Set theory formalized infinite collections. Topology studied continuity. None of this would exist without questions like Zeno's. Not just his questions, but questions of that type. Hard conceptual problems requiring new mathematical frameworks. He changed how we think about change itself. Not just motion, any transition. How does anything go from one state to another? When exactly does water freeze? When does a decision get made? When does a person become responsible? These involve similar issues, continuous processes, discrete outcomes, transitions that seem instantaneous but must take time. Zeno's territory. The paradoxes persist because they touch something fundamental. The relationship between discrete and continuous, between finite and infinite, between our concepts and reality. These gaps are permanent. We can narrow them. We can't close them. So Zeno's puzzles remain relevant. Different solutions, different frameworks, same underlying tension. Modern interpretations keep appearing. Each claims finality. Each gets challenged. The cycle continues because there's no obvious stopping point. Mathematics handles the calculations. Physics makes predictions. Philosophy asks what it all means. Different standards for different fields. No consensus on what counts as resolution. Maybe that's fine. Maybe some questions aren't meant to be solved. Just better understood. Each generation takes another pass, clarifies something, adds nuance, sees connections previous thinkers missed, progress without completion, understanding without finality. Zeno started this. One man, one lost book, ideas that outlasted empires. The Greek city-states fell. Rome rose and collapsed. Medieval Christianity dominated, then declined. The scientific revolution transformed everything. Through it all, these paradoxes remained, still discussed, still debated, still generating new mathematics and physics and philosophy. How many thinkers achieve that? How many ideas survive 24 centuries and stay vital? Not many. Most philosophy ages, becomes historical curiosity, interesting for what it tells us about how past people thought, not relevant to current problems. Zeno's different. His paradoxes aren't museum pieces. They're living puzzles. Each new framework for understanding reality has to address them. Each new theory about space and time faces Zeno-like challenges. Quantum gravity, string theory, whatever comes next, they'll all encounter versions of his questions. Because the questions are fundamental. What is motion? What is continuity? What is change? These aren't about specific physical systems. They're about the basic structure of reality, how things can be different at different times while remaining the same things, how transitions happen, how the world works at the most basic level. We don't have final answers, we might never have them, but we keep trying, keep building better theories, keep testing them, keep finding where they break down. That's how knowledge advances, not through final solutions, through progressive refinement, better approximations, deeper understanding. Zeno showed us what needed understanding. He revealed complexity beneath simplicity, mystery beneath the obvious. That's philosophical achievement of the highest order. Not explaining everything, showing what needs explaining. Not resolving all doubts, demonstrating where doubts are justified. 24 centuries. The man is gone. The book is lost. The school is forgotten. But walk across a room and you're engaging with Zeno's ideas. You're completing an infinite series, traversing uncountably many points, accomplishing what his paradoxes said was impossible. The math explains how, philosophy asks why, physics tests predictions, and we're all still working on it. That's what he left us. Not answers, better questions, not solutions, permanent puzzles, not certainty. Honest acknowledgement of how strange reality is once you examine it carefully. The obvious isn't obvious. The simple isn't simple. Motion happens. But explaining how requires mathematics that took 2 millennia to develop. And even then, the explanation raises new questions. Zeno of Elea, born around 490 BC, died around 430 BC, wrote one book, created 4 paradoxes we still discuss, changed philosophy, influenced mathematics, anticipated problems in physics, all by thinking carefully about runners and arrows and tortoises. No experiments, no equations, just logic. Just asking what motion actually is and showing our answers don't work. 24 centuries later, we're still grateful, still learning, still finding new depths in problems he posed before Plato was born, before Rome existed, before Christianity, before science, before calculus, before modern mathematics, before everything we use to understand motion now. He saw the problems first, with nothing but thought. That's power. That's why he matters. That's why we remember him when thousands of his contemporaries are forgotten. The paradoxes are immortal because the questions are permanent. And permanent questions honestly asked are worth more than temporary answers.